So we're going to talk about the cooling of a ball, a classic problem where we take a ball of some homogeneous material and heat it to an even temperature all the way through, and then fix the outer surface equal to 0 and watch how it cools. So this is similar to a Newton's law of cooling type problem, but in Newton's law of cooling, the temperature distribution inside the object is ignored. It's just assumed to be uniformly the same temperature all the way through as it cools, which is, of course, not true in any physical system. So let's start with the heat equation. So we've got UT is equal to K Laplacian U, and we will think of this as as a spherical Laplacian, and we'll take this as the radius rho is varying from 0 to pi. Pi will just conveniently make things a bit simpler. And we'll take our function also to be spherically symmetric. So let's see. So the temperature on the surface is fixed equal to 0, and then we will have u just as a function of rho and time, so it's spherically symmetric, is t0. So this is how it this is for time equals 0. So this is the initial temperature at which the ball is uniformly heated. There's also an implied boundary condition that U is going to be bounded on the entire ball, but in particular at the origin, which is where it will come up. So in this context, again, the Laplacian of U is going to be U rho rho plus 2 over rho U sub rho, and the phi and theta terms don't show up because of the spherical symmetry. That's what spherical symmetry means. Depends on nothing but radius. Okay, so we'll make our standard separation of variables assumption that this function of rho and t splits into some function of rho alone and some function of t alone. So substituting this into our equation, we end up with g prime over kg equals y double prime plus 2 over rho y prime over y equals minus lambda. And then from this separation equation, we get g prime equals minus lambda kg, and y double prime plus 2 over rho y prime plus lambda y equals 0. Okay, and so the first one we can easily solve. It's going to be some constant e to the minus lambda kt as usual. For the second one, let's see. Well, first off, the spatial boundary conditions roll over exactly onto y, just like they usually do. So this one needs to be 0 at the outer boundary. And then also the fact that it's bounded also affects only this one. So then we solve for the y equation case by case. Our first case being, let's look at when the eigenvalue is equal to 0, or when lambda is equal to 0. Do we get any eigenvalues? So in this case, the equation becomes y double prime plus 2 over rho y prime equals 0. And so this guy is separable, or you can solve it as a Cauchy-Euler equation, or you can solve it as a linear equation with an integrating factor by substituting v equals y prime. Any way you want to do it, you will end up with y equals a over rho plus b. Now, because y is supposed to be bounded at the origin, we know that this is going to just be a constant. But then if we look at the boundary condition, then we get that y equals 0. And so that gives us no eigenvalue at 0. Okay, so then what about if we have lambda non-zero? Okay, so if lambda is non-zero, then it's not immediately clear what to do with the differential equation. But if we make the substitution v equals rho y, so that y is rho inverse v, then substituting this into the equation, everything cancels in this amazingly lovely way, and you just end up with rho to the -1 times v double prime plus lambda rho inverse v equals 0. And then you can cancel the rows because those are not going to zero out your formula. And so you just ended up with v double prime plus lambda v equals 0, from which you can continue the analysis. So if we look at the subcase of when lambda is positive, then we have that well, v is going to look like a cosine rho root lambda plus b sine rho root lambda, which means that y looks like 1 over rho times this same thing. And then let's see. So once again, since y is bounded, when we look at rho equals 0, you can see that this term is going to try and make things diverge. Now, it will make the cosine term diverge because cosine tends to 1. But sine of rho over rho actually tends to a finite constant, because sine x over x tends to 1 as x goes to 0. So this tells us that a has to be equal to 0, and so y looks like b over rho sine rho root lambda. From the boundary condition then, we find that the eigenvalues are just going to be the square integers, non-negative ones anyways, and that our YNs are going to be sine n rho over rho. And so putting this back together, well, okay, so side note, it turns out that when you go to check the case for lambda negative, you get no eigenvalues. So then, putting all this together, we see that u of, oops, not r, wrong radius, that should be rho. U of rho t is going to be the sum from 1 to infinity of Cn times our g function, which was e to the minus lambda kt, but now we know what lambda is, times sine n rho over rho. And so here for the Cn's, well, actually here, let me back up. When we evaluate this at time 0, then we have the initial condition, and we know that t0, so that's our u rho 0, is going to be given by Cn sine n rho over rho. because the exponentials drop out, as usual. So, okay, so let's take a look at this guy. Now, rho does not depend on n, so I can multiply it over to the other side for simplicity. And now we're just computing the Fourier sine series for t naught rho. And so that looks a little bit funny. There we go. And so now you just have to compute those coefficients, and it turns out that Cn takes the form t naught negative 1 to the n plus 1 times 2 over n. And so that's what we get for our formula here. Actually, let me put the constants out front. 2 times t naught summation negative 1 to the n plus 1 over n e to the minus n squared kt sine rho over rho. And that's our guy.